Okay, fine. I'm Dr. George, Professor in Civil Engineering, currently associated with JB Institute of Engineering and Technology, JBIET, with JNTU, Hyderabad. I've been a professor for about 15 years and I've been in teaching profession for 30 years in all, out of which the first 23 years have been in Pune University. And in addition to that, after my Pune University tenure, I worked in Kerala, in Andhra Pradesh, and presently in Hyderabad. And all through my professional career, I've been teaching structural engineering related subjects, right from engineering mechanics to mechanics of materials to theory of structures and that series at the undergraduate level, and then finite element methods and structural dynamics at the postgraduate level. So right now, as a part of FDP, that is Faculty Development Program, I'm addressing my colleagues, 18 of them, and this was taken about 2 months ago. So I just wanted to introduce certain things to my faculty, to my colleagues, so that they can make it percolate to their students as in how they handle their various courses. A new look at basic structural analysis. So the session is titled, all these sessions are titled a revisit to basic structural analysis. A revisit to basic structural analysis. Now, what do you mean by revisit? Revisit means we need to take a fresh look at the way we look at the very word basic structural analysis. Now, what is basic and what is analysis? Structure, of course, we know what it is, or structures, what they are. What is basic? Basic is not SFD and BMD, and that's what we as a faculty community tell our students. That's not the case. So basic is somewhere else, and analysis, again, we need to take a fresh look at it. What do you mean by analysis? Analysis is not just drawing the SFD and BMD or the torsional diagrams. That's not analysis. There's something much before that, and that is fundamental, and that is basic, and that is M, L, and T, some high school stuff, matter, space, and time. Because if I apply a force on something, if I apply anything, generalized force system, any kind of force, any kind of moment, any torque, whatever you call it, you may be drawing beautiful diagrams. That's fine. But the structure doesn't know what kind of diagram you are drawing. The structure knows only one thing. Structure knows only deformation. And it is deformation that dictates everything. Your strain, your stress, your bending moment, your shear force, your torsion, whatever. Everything is dictated by the deformation. So why don't we think about a basic structural analysis that is based on very basic deformation. So the whole thing, I'm just restructuring it. The whole basic structural analysis should be fundamentally based on deformation. So there we go. You got a matter. It is subjected to force. That means you got an M. You got another M acting on it, or derivative of M acting on it, and then you got deformation. That is space L, which may or may not vary with time. So M, L, and T, everything are coming into picture. So let's start with, if you leave that time alone, as in civil engineering structures, we generally don't deal with time, unless of course we go into earthquake engineering and things like that. So the fundamental idea is to establish a relation between space on space in relation to matter. That is the force acted upon. So I wanted all my colleagues, or rather I want all my colleagues to make it percolate to their students through the courses they handle. I mean, just a basic. It's not going to create a revolution, but it's going to make a fundamental difference in the way they think about structural analysis. That it's not just of SFD and BMD, though they carry very high meanings. That's fine. As far as the designs are concerned, they are very important. But deformation is not something to be neglected. After all, it is from deformation that everything else follows. So this is what I would like to convey. I'll be just looking at basic structural analysis from the very fundamental. That is deformation response first, and then only your force response, and not the other way. Because we are just questioning the integral path that is followed in basic structural analysis. That means everywhere you have got all kinds of methods wherein bending moment is almost supposed to be a prerequisite to find out the deformation. That's not the case it is. The case is deformation comes first and then you derive what you want. So we are following a differential path, that is y equal to f of x. You got a structure, you define the space coordinates for the structure, and then you find out whatever you want. That is the slope, the moment, the shear force, everything. So the route is different. It is from integral path to a differential path, or rather integral path is being questioned and differential path is being established. That is the very fundamental of it. So you'll find it little awkward by defining the equation of the elastic curve of a structure first. And I'm talking about the bending theory, everything that follows bending theory. So we will just have y equal to f of x defined first, and then you have your y dash, y double dash, y triple dash, and y 4 dash, everything. So that's the way it goes. Take a look at it, and you'll find slight oddity in it. I mean, the way it is, because it is completely against or completely in contrast to the conventional methods. No conventional methods will follow this path. All conventional methods have got integral path. You first have bending moment and then you reach deflection. No, we'll define deflection first and then come to bending moment and shear force, things like that. So take a look. I know where we stand. We are closing in on SFDs and BMDs, but before that there is something more fundamental. How curves behave. This is a curve y equal to f of x. Now, what's the speciality of this point, and this point?
Changes direction.
Changes direction. So mathematically, how do you express? dy by dx
Equal to 0.
equal to 0. Okay, I'll do that. At point A, point B, and point C, dy by dx equal to 0 at A, B, and C. Fine. What's the importance of this point and this point?
Negative and positive. Inflection.
Yes. Now, I hope dy by dx need not be explained. All of you know what is dy by dx. So, here dy by dx, is
Negative slope.
some things that you have to test properly. d by dx. There is nothing special about d by dx. Just tell me whether it is positive or negative.
Negative.
It is negative. Yeah?
Positive.
Positive. So there is no speciality for d by dx, but there is a speciality for something else. Okay. Here it's a positive slope. Here also it is a positive slope. Here, when positivity is increasing, positivity is further increased and becomes 0. Then it goes to the negative side. Negative, higher negative, higher negative, higher negative. Now, what happens from here onwards? 0, mild negative, little more negative, more negative, more negative. Now, here these are all negatives, but the rate at which that negativity changes has changed. That means, what has changed? The rate at which the negativity changes. Now, negativity of the slope. That means d squared by dx squared. Rate of change of slope has changed. That means d by dx of d by dx. This is the catchword, has changed. Has changed means the rate at which has changed from what to what? From here to here, it was negative, more negative, more negative. Now it is becoming less negative, less negative. Right? Until it becomes 0. So it has changed. Means d squared by dx squared equal to 0. The catch is not that. This is what the textbooks will tell you. But that is not sufficient. Because it has changed sign. And such points are known as
Point of contact.
no, don't talk about sectors. We are not. It is point of inflection. It is point of inflection. So this is the most important thing. It's not necessary that, or rather, it's not sufficient that it is 0. d squared by dx squared has to change sign from positive to negative, or from negative to positive. Here things are different. Positive slope, positive is increasing, positivity is increasing, positivity is increasing, and here also now it is positive, but now positivity is decreasing. So it has changed from positive to negative, and here it was negative to positive. Now, I still repeat that. Consider it go like this. That d is equal to 0 and d squared by dx square is less than 0. It is called what point? Maximum. Wrong, it is local maximum. That's important. I will tell you the importance of that. Local maximum. See, this is a local maximum. This is a local maximum. This is a local maximum. A, B, and C. Local maximum. And D and E. What is that? dy by dx equal to 0. D squared by dx square is greater than 0. That is local minimum. Please focus on that. D and E. D and E. And of course, these points, I'm not marking it again, those are all what points? Points of inflection. So there what will happen? dy by dx, no speciality, they will be all non-zeros. But this is a point of this thing, so don't. Here I wanted to focus on something. The routine way of teaching calculus is my बिजली आज ऐसा मैं सैटरडे को मुझे बहुत डर लगता है. 2 सैटरडे को काफी देर लाइट नहीं था. ठीक है. Anyway. It's good question. If I want to join this by, okay, I make it simple. What is the order of a polynomial that will contain these 2 points? Straight line. Now come to that. Okay, straight line. That means I get the answer from you. What the order of that polynomial is what? Straight line. Straight line का order क्या है? One. It's order of 1. So now tell me. Third. And all of you have learned rigorously and you have scored marks also. And it is the best polynomial that fits it. Whose polynomial? There are so many great men who will go for this. When you do Lagrangian interpolation, what you are doing is that your teachers would have told you, you are actually fitting a curve without your knowing it. Yeah, I'm sure these things are not taught. I am of the opinion that mathematics should be taught by proper engineers who understand mathematics. And when I say you cannot teach mathematics, you cannot learn mathematics, you have to discover mathematics. So, this could be a curve. Now, Lagrange will be interested only, his only intention is that curve will pass through this 4 points. Afterwards, it will behave bizarrely, that we are not bothered. So, you use your Lagrange interpolation so that because you have so many data, you have to fit it, and he will probably fit it in between. But you can't extrapolate. Lagrange's polynomial is inefficient for what? For exponential. We can't go beyond the limit. Which means we are given x value, y value 2, 3, 4, 5, something like 7, 11, 13, 15. Polynomial will fish at x equal to 2, it is 7, all those things. In between 2.5, it will give excellent values. But don't ask the polynomial to give the value at 6 or 1. There it will fail because you have no idea how the curve is going to behave.